Hey y'all, Rusty Rob here. Welcome back to another video. I've got a really exciting problem, a really difficult problem from the New Zealand Programming Contest last weekend. And thanks everyone from the NZPC who subscribed to the channel. It was nice meeting you all. And hopefully Phil will send this out to a few people. I'll email him the video after. Just before we get into the problem, a little announcement. Thread, who sponsored our team for the NZPC, we are hiring. So if you're looking for an internship this summer, definitely apply. And I think we'll be growing the team quite a lot next year. So just be on the lookout. It's a really exciting product and space that we're building within. Internet of Things and smart factories and crunching a lot of data on the cloud and like real-time processing and things like that. So yeah, look us up and get in touch with me. Add me on LinkedIn or something. So this problem, it's basically a reservoir full of water, but there's also some brick walls within the reservoir which kind of trap the water into different puddles and things like that. And so you're tasked with removing a brick from the outside of the reservoir to drain as much water as possible. So it's quite a challenging problem because water will flow, the direction the water flows kind of depends on which brick you remove. So that makes it really hard to get an efficient solution. And it's a 500 by 500 by 500 reservoir, so it's a lot of cells. So you need to process it really efficiently. And you can see the reservoir above is represented by this 2D grid, where each cell represents the height of the bricks at that point. And the answer is 63. And when I run this, I get 63. So awesome, we got the right answer. And I'll provide this code in the comments. I'll link to the GitHub. But yeah, let's talk about an approach. So you could depth first search from each edge point of the reservoir and just keep track of the height, so you're only ever going upwards and seeing how much water can flow in. But that would be, well, I guess there's, n edge points, let's say. So you're potentially doing, that would be n cubed, or maybe n to the power of 4, depending on how you implemented it. So that would be too slow. We actually tried a Rust n cubed solution during the contest and hit the time limit. So we thought the time limit was 5 to 10 seconds, but it turned out the time limit was 1 second. So it was just too slow. But we did have another idea of an approach, and so that's what I'm going to show you today. So to get a really efficient n squared solution, so 500 squared solution, so we only have to look at each cell once. We have to be kind of clever with how we track how water could potentially flow and take all potential flows into account at once. So if we think about some puddles, right, some just small puddles, and think about how would they grow as you add more water. Well, they will keep growing. Eventually they'll merge into each other, right, and they'll become like one larger puddle, and that might become like a larger puddle, and so on. So it's kind of interesting. How can that help us get an approach? Well, if we looked at the puddles at each height, and as we increase the depth from depth 0 all the way to depth 500, we could look at like a cross section of the puddles as they're growing and like add those slices or those areas to the volume, and so you'd be building up volumes from below. But then how do you know if you're connected to an outside edge of the reservoir, and so on? And it gets tricky in other ways as well. So so the trick is to represent it as a tree, and to realize that you can represent it as a tree. So if I have this little puddle here, let's just say it's got a certain height, which I'll call like DH. And then that's it within a larger puddle eventually. So it's completely submerged. Then I guess the trick is that any water from this larger puddle would flow into that smaller puddle, right? And this large puddle could have hundreds of smaller puddles within it. Let's just say it's just got two, because it's easier to draw. And some of these puddles could be on the edge, some of them might not. But we can see this looks a bit like a tree, right? And this could be part of a larger tree. And so the amount of water that will flow into a puddle is the amount of water that flows into the parent puddle plus the surface area of the puddle I'm currently at multiplied by the height of the current puddle. So let's just put a few labels in. Let's call this like height of a puddle is DH, and let's call the area of the puddle my area. I should have called it surface area or something, but that's just what I've got it in the Python code. And we'll call this parent volume. Alrighty. So you can kind of see, starting at the top with the parent volume of 0, we could traverse down using depth first search, breadth first search, and calculate the volume of each puddle, and then pass that volume down recursively. So we're kind of aggregating those volumes, and we can send it both ways. So we're not recalculating. That's why we would kind of want to go from top to bottom rather than from bottom to top, because if you go bottom to top, then it gets pretty messy and you don't know the volumes and things. But this is still going to be really difficult. Like, how do we build this tree efficiently? So I guess I'll explain how to build this tree. And in my implementation, you could see this tree has a maximum height of 500, but in my implementation, I make every single cell a node in the tree. So my tree is maybe potentially a lot taller than this, but it's the same kind of principle. There's like an edge case you'd have to worry about where, say you have a puddle that looks like this, then you have like some low points in here, and then these higher walls. Then where is the parent? Like potentially like that flows to there, which flows to there, and so on. So yeah, it's a bit messy. But as you're building up a puddle, let's just say you've got cell 1, and then, well, let's just say you've got a puddle which has got nodes 1, 2, and 3, and you've got another puddle here called A, B, and C. So we could use two lists to represent these puddles and just merge them together, A, B, C. But because we might have to merge that again with another puddle and again, then each of these puddles could be merged many times. So it might be too slow. The cost of merging, you don't want the cost of merging to be the cost of the size of the puddle or the number of elements of the puddle. So instead what we'd do is we'd have this puddle 1, which also had cells 2 and 3 within that puddle, and they just point at an arbitrary parent within that puddle. And then similar for A, B, and C. And if we want to merge these two puddles into a larger puddle at a certain depth, then we just point them to we point one parent to a parent of the other puddle, and so each puddle just can be identified by the parent of this tree. And you can see we could have like another massive puddle with 1,000 items here, and to merge the two, all we have to do is add one arrow. So that means it's an order one operation to join two puddles together. And then eventually you might get quite long paths. So to find the puddle that an item is in, you just go to its parent, and then its parent's parent, and then its parent's parent, until you get to the top, and then that gives you the ID of the puddle. And then you do path compression, which means now we do a direct arrow from here to here, and a direct arrow from here to here, because we found the parent. And so you end up getting a really flat structure, kind of like this. You'd have 1, and then you'd have 2, 3, A, B, C, all pointing to the one parent. So we keep flattening this tree, and so that's how we can use, I think it's DSU or union find algorithm or something like that, to merge these sets efficiently. So let's just jump into the code. I'll put this in presentation mode. And to all my Rust followers, sorry that this is Python. I did add Python to the DOM judge so that people could use it in the NZPC and ICPC World Finals and things like that, but just for testing this I had to use Python. It's like an old judge. Right, so we've got the solve method. You can see I'm setting the recursion limit because our tree can be pretty big. And then I'm just reading all the lines from standard input and getting an array. For each line I'm just making it a list of ints. And then we're scanning the number of rows and columns and the height of the grid, and we're just grabbing the grid, which is just for each row we just want a list of integers. And then I decided to convert that grid into a graph, an adjacency list, just because it's a bit easier to work with. And so instead of having an R by C grid, I just have a graph of n adjacency lists and n heights. So for that I just assign each cell a unique ID from 0 to n using this hash function. And I'm only adding edges to a node's adjacency list if the height is less than or equal to my height. And so this is just all the ones horizontally next, before and after, and vertically before and after get added. And then we're just tracking the heights as well, and also tracking a set of edges for later, because you can only remove a cell from the edge. And then we've got this DSU data structure, which just for every puddle the parent starts off as its own parent. So the parent of 0 is 0, parent of 1 is 1, and so on. And each puddle just has size 1. And we can use that size later on, as the surface area of a puddle is just the number of cells in it. So yeah, to find the ID of a puddle, we just find the parent, and if it's equal to itself, then okay, we're at the top of that puddle. Otherwise we just recursively keep going until we get to the top, and we set that at the same time. So that's the path path compression we were talking about, and then we return the ID of that puddle. And to join two puddles together, so we just find the parent of each puddle. If they're equal, we're done, they're already been merged. Otherwise, we set the parent of one puddle as the parent of the other puddle and just increase the size of that puddle by the size of the other puddle. Okay. Now I'll go through this recursive function last, I think. So yeah, we get our grid, we convert it to a graph, which is just a bit easier to work with. And we want to go through the, oops. Not sure why Google Assistant's talking to me all of a sudden. That was a bit odd. Alright, so we want to go through all these nodes in order of height. So we're just gonna start off with our order, which is just a list of all the indices in the graph, and we'll just sort it by the height attribute from the height array. So each index has its corresponding height, and so that's the key function that we'll sort by. And if this was Rust, I'd use sort unstable by key, or sort by key unstable. And yeah, because we only have 500 different heights, this should be pretty efficient. I mean, you can use bucket sort if you want to make sure that this is order n squared instead of n squared log n. Just tracking which nodes are visited, initializing a tree. Initially, every node has no children, and initially every node is a parent, but whenever it gets added to the tree, then it's no longer a parent. So we are left with just one parent, which is just one of the tallest cells, highest height cells. Yeah, so we go through every index in order. So the low cells first, lowest to highest. Set it to visited, and then we find its puddle, which is just P. You can think of P as parent or puddle. And then for each index in the graph, so it's got up to 4 child nodes that are smaller or equal to it, or like lower down. So we know those have already been processed, unless it's this equal in height, and that's just why I put this visited array here, because it could be the same height as me. So he might have already processed it. So if we've processed that node already, then we grab its puddle, and if they're not already part of the same puddle, because when visiting that particular cell, we could have already added me to the puddle, the current node to that puddle, if it was equal height. Anyway, so yeah, if the puddles aren't equal, and that's also, I guess, yeah. So then we'll just know that puddle was kind of tacked onto this current cell. So we're kind of adding it to the tree, and then we'll just union those puddles, and that'll increase the size of this one by the size of this one, as you saw just here. And then yeah, we know P2 is no longer a parent because we added it as a child of P. So yeah, just asserting that there's only one parent left, and so we just grab that parent, and then yeah, we recurse, and we get our answer. So to recurse, we just have the parent, or the current cell that we're at, and we have the array of heights, so that we know the height of each cell. We have the sizes of each puddle. We have the tree, and we start off with h minus 1 because that's like the top of the reservoir, and we start off with a parent volume of 0 and some edges. The set of edges is just so that we know, I'm getting quite a few messages. sure why Google Assistant all of a sudden started giving me a whole lot of notifications. It's never done that in the past. Anyway. So yeah, the edges was just a set of edges, so we could track when we can potentially remove a brick. So yep, at each puddle we get our area, which is just the number of cells that were in that puddle when we did union find at that point. And then what was this? This was the change in height, so DH, or the delta in height. So it's just the parent height minus my height. So we know that this is a positive number. And the trick is, in my implementation, that this can potentially be 0. So we can have nodes of the same height connecting to each other. I won't bother drawing that out, but basically our tree visits every single cell. And that means that this step will work as well. So yeah, the volume will just be equal to the parent's volume plus my surface area times all the height that's going up to where the parent puddle started, which you saw in that initial diagram. And so yeah, the answer is 0. But if I'm an eligible edge, then the answer will be my volume. And then so for each child in the tree, then the answer would just be maximum of if we removed the brick at my level versus if we were able to do it at any of the child puddles. And then we just return the answer. So that was that. I thought that was a really fun problem. And I think this problem is really easy to go wrong. Like, you really need a really simple implementation and to just think carefully about each thing. But in the end, it was I thought a pretty elegant solution. So well done whoever came up with that problem. It was a really fun problem to work on, and I saw quite a few teams attempted it, but a lot of them got the time limit exceeded. And I even talked to one high school kid after the contest that solved it, so well done, that's pretty impressive. It was great to see so many high school students at the contest. But yeah, I might do another video later in the week for problem O, which was where you had to find the shortest path from one side of a graph to another and then back again, so it was like a loop without visiting the same edge or node twice. So that was a really interesting problem, which I think you can use Darktrace for, so we'll maybe have a look at that. But so please subscribe if you're keen on seeing a few more videos like this and a few more Rust kind of general programming videos. And if you know anyone that's looking for a summer internship, tell them to get in touch as soon as possible. Thanks for watching.